Hello everyone, welcome to Unit 27 of online course on probability distribution. So far we have introduced binomial distribution, Poisson distribution, geometric distribution, negative binomial distribution. And now we are introducing a new distribution known as hypergeometric distribution in this module. Hypergeometric distribution is a distribution in the family of discrete distributions. And when we have a population that consists of two types of objects, which we will refer to as type 1 and type 2. For example, a batch of components that are either good or defective, or a population of people who are either male or female, a population of animals that are either tagged or untagged. Or suppose we have a box containing two types of balls with the color white and black. So such population we have consider, and from that population we are finding the probability of an event happens k times in n trials when you are sampling from that population, and this type of population usually known as dichotomous population, that is two category, defective or non-defective, literate or illiterate, okay, then that male or female, or such a population, dichotomous population, and we are sampling without a replacement, and we are finding the probability of an event that happens k times in n trials. If that is the situation, what type of probability models are used to model that particular random variable? That is our question. So hypergeometric distribution is actually similar to binomial, because binomial distribution, when we are discussing binomial distribution, we have Bernoulli trials, and Bernoulli trials means either success or failure, or defective or non-defective, literate or illiterate, dichotomous. Okay, so this distribution is like the binomial distribution except for the sampling without a replacement aspect. Note that when you sample without a replacement, the probabilities change with each subsequent trial, whereas the binomial distribution assumes the chance remains constant over the trials. When we are discussing binomial distribution, we know probability of getting success is constant throughout the trials. But when we are considering a probability model in which we are considering the sampling without a replacement, the likelihood or the probabilities of getting a particular event is changing over the trials, because we have, suppose we have a population consisting of defective and non-defective items. So suppose you are selecting an item, and if it is a defective one, then in the remaining population, the number of defect is reduced by 1, or the total item also is reduced to 1 by 1. So the probability of getting a defective in the next trial will be different from the probability of getting a defective in the first trial. And the hypergeometric distribution can answer the questions like what is the probability of drawing 5 cards of the same suit from a regular packet of cards, playing cards, or what is the probability or what is the likelihood of getting 3 women on a jury of 7 people when drawing randomly from a jury pool of 20 people, which are evenly split between men and women. So this type of problems, that is, as the population sizes increases, the hypergeometric distribution more closely approximate the binomial distribution. So already we have the binomial distribution concept. So we are addressing the questions or addressing the problems like what is the probability or what is the likelihood of getting 5 cards of the same suit from a regular deck of cards, or what is the probability of having 3 women on a jury of 7 people when drawing randomly from a jury pool of 20 people, etc. And here, when the population size increases, this hypergeometric distribution is more closely approximated to binomial distribution also. And how do you explain or the probability mass function of the hypergeometric distribution? So consider a random experiment of selection of n items without replacement, of course, from a finite population consisting of m items of one kind and n minus m of second kind. Then what is the probability of getting k items of first kind? This question is addressed here. So a random experiment of selection of n items without replacement from a finite population consisting of m items of one kind and n minus m of second kind. That is, you have, so we have a population of 2 types of items, type 1 and type 2. And suppose type 1 item n items are there and type 1 m items and type 2 n minus m. So total m items. And we are selecting n items from here. We are selecting n items from here. And suppose k items of first type and of course n minus k items of the second kind. So this is the problem. Consider a population comprising of 2 types of items, m of first kind and n minus m of the second kind, and so the total is n. Total is n items. So we have total n items, and getting k items of type 1 and getting n minus k items of type 2 when we are selecting n items without a replacement. So usual probability definition gives what is probability of getting x is equal to k. Suppose x is the number of items of first type So x we defined as number of items of first type. So probability of x is equal to k is what? Favorable case of getting k items from type 1 consisting of m items. So we are selecting how many items? We are selecting n items. So of course, the n minus k items should be from n minus m items. So that are possible in n minus m, c n minus k different ways, divided by total number of ways. What is the total number of ways? Capital N C n. So remember, when we have a population having different two types of items, and suppose the population consisting of n items, of which m are of type 1 and n minus m are of type 2, what is the probability of getting type k number of type 1 items? And that probability is obtained by mck n minus m c n minus k divided by ncn. So this is the probability of value obtained using the usual definition of the probability. Now, favorable case divided by total case is the definition we are using to find the probability. So that is mck n minus mc n minus k ncn, where k is any value. Remember, k is that we have total n items. We have total n items and m items of first type and n minus m of the second type. N items of which m are of type 1 and n minus m are of type 2. So k probability of x is equal to k is equal to mck n minus m c n minus k divided by ncn, where k is equal to 0, 1, 2, etc. up to. Remember, maximum value is, which is the minimum of number of total items, it is n, or capital M, that is first type. So suppose we have 10 items of which 3 are of first type and 7 are of the second type, and we have selecting 4 items. What is the probability of getting k items of first type? So here this 3 and 4 are, consider the minimum is 3. So this is our minimum 3 is taken. So that depends, k value, the maximum value of k, depending upon the minimum of concept, minimum of small n, that is total number of items selected, and capital M, that is the total number of type 1 items. And this probability is our probability mass function of the hypergeometric random variable. For example, a consignment of 50 light bulbs contains 5 defective and 45 non-defectives. A quality control inspector randomly samples 4 bulbs without replacement. Let x be the number of defective bulbs selected. Find the probability mass function effects of the random variable. So this is a usual question in the probability chapter, elementary probability chapter. But remember, the probability value corresponding to this type of problems is actually our probability mass function value of the hypergeometric random variable. So here what is the situation? We have a consignment of 50 total items, 50. So we have 50 items are there. And 50 of this 50 items, there are 2 type of items. One is defective item and another non-defective. And there are 5 defective items and 45 non-defective items. Okay? And a quality controller inspecting bulbs randomly without a replacement. That is, he is selecting the item and verify whether it is defective or non-defective, and that bulb is not replacing into the consignment. And X be the number of defective bulbs selected. So what is the probability mass function? So suppose X is equal to K, we are finding. Probability of X is equal to K. X is what? X is the number of defective bulbs selected. What is that? We have how many bulbs are selected? 4 bulbs are selected. So we have the total case 50 C4 cases. A quality controller inspecting 4 bulbs. Okay. And now the defective bulbs are 5. So 5 CK. The K is the number of defectives. And 45 non-defectives. And so it is 45, sorry. We are selecting 4 bulbs. So 4 minus K. Okay. So we are selecting 4 bulbs and K of which are defective, and that defective bulbs are obtained from the 5 defective bulbs in 5 CK ways, and there are out of 4 total bulbs, how many will be non-defective? 4 minus K will be non-defective, and that are from non-defect total 45 non-defective bulbs. So 45 C 4 minus K. So this is our, and what is K value? What are the possible values of K? K is equal to, it may be 0, it may be 1, it may be 2, and see, we have selecting 4 bulbs. So minimum is here, minimum of N and M. We have the upper value of K is minimum of N and M, and here the M is 5 and N is, we are selecting 4. So remember, so the maximum maximum value of K is minimum of 4 and 5, that is our 4. So this is the probability mass function of this particular experiment, and this is the probability mass function of a hypergeometric random variable. And another example, just consider X be the number of asses, ass cards. We are selecting 5 cards from a pack of playing cards. Find the probability mass function of X. Here also we have a pack of playing cards, and playing cards consisting of total 52 cards. And that 52 cards are of 2 types. We are considering as and non-as. That way we are classifying. And how many as cards are there? 4 cards are there. And how many non-as cards are there? 48 cards. X denote the number of asses in 5 card hand set. So how many cards are selecting from 52 cards? 5 cards are selected. So this is the problem. So we are having a pack of playing cards consisting of 52 total cards, of which 4 are of as type, and remaining, that is 52 minus 4, that is 48, are non-as cards. and we are selecting 5 cards. Then write the probability mass function of x. What is x? Here the random variable x is the number of ass cards obtained. Number of ass cards obtained when we are selecting 5 cards from a pack of playing cards without replacing. So, what is the probability of x is equal to k? Here also you just see what is the total case here. We have 52 cards total, 52, and how many cards are selecting? 5. So, total case 52C5, of which suppose 4 ask cards are there and k are not obtained. So, 4CK, and 48 non-ask cards are there, and we are selecting 5 cards, so it is 5 minus k. See? So, this is the probability of getting k ask cards, and what are the possible values of k? It may be 0, it may be 2, 1 or 2, etc. up to where? Minimum of n. N is here. The how many cards are selecting? 5. And of the first type, what? 4. So, this is minimum is 4. See? Okay. So, k is equal to 0, 1, 2, 4. So, this is also an example, that is the usual elementary example in the case of probability section. But remember that this is a problem associated with a hypergeometric distribution. Okay, and now we consider what is the mean value of the hypergeometric random variable. Very easy to obtain the mean value. Usually we know the expectation of x is obtained by sum over x, x into f of x, and f of x value we have n mcx n minus m c n minus x divided by n c n. So, if you are writing in terms of x, this is the way, or in terms of k, we have this is, I think it would be better to write x here. Okay. So, sigma over x is equal to 0 to n x mcx n minus m c n minus x c n minus x divided by n c n. And remember, this is equal to, this NCN is not associated with the summation, so taken outside. Let me write this as m minus 1 c x and mcx you consider, that can be written as x into m factorial divided by x factorial into m minus x factorial, or that is m factorial divided by x minus 1 factorial m minus x factorial, and that can be written as m into m minus 1 c x minus 1. That way we can write. So, that m is taken here, m divided by NCN and m minus 1 c x minus 1 n minus x. Okay. So, if we are representing the probability mass function in terms of f of x, do not write k. If you are representing in terms of probability of x is equal to k, represent in terms of k. So I am representing f of x here. So this is mcx n minus m c n minus x divided by ncn. And simplifying this expression, we can write like this. And what is the advantage of writing like this? See, this is what? Sigma over x is equal to 1 to n mc m minus 1 c x minus 1 n minus m c n minus x. You know that is nothing but mc m divided by ncn m minus 1. You can write it as, and k dash as k minus 1. In the previous example, that way you can write. And then m dash c k dash and the n minus 1 minus m dash n minus 1 minus k dash. And this is a standard expression for us, and that value is equal to n minus 1 c n minus 1 by the argument that summation of the probability mass function is equal to 1. Earlier we discussed that one, sigma over f of x is equal to 1. Based on that, this value here it is this is the parameter. So that is why this is n minus 1 c n minus 1. Simplifying, that value is equal to, so m divided by ncn n minus 1 c n minus 1, simplifying you will get it as m divided by n. And similarly, so for a hypergeometric distribution with the parameters n, capital M and capital N, mean is equal to n into capital M divided by n. Similarly, we can find the variance, and to find the variance, first you find the expectation of x into x minus 1. Here also the problem is similar to the earlier procedure. Expectation of x into x minus 1 you find, and that is sum over x is equal to 0 to n x into x minus 1, and again here this not, because we are writing all the expressions in terms of x. So sigma x is equal to 0 to n x into x minus 1 mcx n minus mc n minus x divided by ncn. And then what we are doing, you consider this x into x minus 1 and this expression together and simplify. So x into x minus 1 mcx, that is m factorial divided by x factorial m minus x factorial, or that is equal to m factorial divided by x factorial and x into x minus 1 factor, cancelling the common factors, you can write x minus 2 factorial m minus x factorial. And that is, we can represent that by m into m minus 1 into m minus 2 factorial divided by x minus 2 factorial m minus x factorial. And that is nothing but m into m minus 1. See, this m minus 2 factorial divided by x minus 2 factorial and m minus x factorial combining, you can write m minus 2 c x minus 2. So that means when we combine those two factors together and simplifying, this expression reduces to this form. So after this we have the value of by making the expression sigma over f of x is equal over all x values f of x is equal to 1. On the basis of that one, we can have the value of the expectation of x into x minus 1 is equal to m into m minus 1 divided by ncn n minus 2 cn minus 2. And that is simplified, you get n into n minus 1, capital M into m minus 1, capital N into n minus 1. See, this is the expectation of x into x minus 1. And generally, see, earlier expression you have n into n minus 1 capital M minus 1 divided by n into n minus 1 our factorial moment expectation of x into x minus 1. And similarly, you can generalize this expression. You can find any order factorial moments, and that is obtained by expectation of x into x minus 1 etc. up to x minus r plus 1 is equal to n into n minus 1 into etc. up to n minus r plus 1 into capital M into m minus 1 into etc. up to m minus r plus 1 divided by n into n minus 1 etc. up to n minus r plus 1. So, remember, this is the factorial moments of the hypergeometric, general expression for factorial moments of the hypergeometric distribution, and these are very easily established, and the variance also we can find here, and using the expectation of x into x minus 1 and expectation of x, we can find the variance. Already we calculated the expectation of x into x minus 1, this one, and expectation of x, this one. So, that is our expectation of x square, and based on this expectation of x square, we can find the variance, that is variance of x is equal to expectation of x square minus expectation of the x the whole square, and substitute all the quantities here, and simplifying, the expression for the variance is this one. These are only simple algebra we are using, nothing complicated. Only thing is that you expand the expression here and simplify, we will get the result n into capital M, capital N minus m, capital N minus small n divided by capital N square into capital N minus 1, where see the small n is the capital N and capital M. What are the significance of this quantities? Just note. You see, this is the total items we have, and this is the type 1 item, and this is the total number of items selected, total selected. So, if M is the type 1, of course, n minus m should be the our type 2. We have a capital N items, total items, of which m are type 1 and n minus m are type 2, and we are selecting without replacement n items, then the probability of getting k of the first type of items is the probability mass function of the hypergeometric random variable, and again we calculate the mean and variance like this, and this is the variance expression of the hypergeometric distribution. Okay, so for the hypergeometric distribution with the parameters, we have the variance like this. So, these are the some simple properties of the hypergeometric distribution, and more numerical problems we can do after this session. So, we will discuss that type of numerical examples in the succeeding sessions. So, we wind up this session here. Thank you for listening. Thank you.